To begin with a brief overview, if you've been with us before on these webinars, just bear with me for 2 minutes. We were founded in 2010 as OES Energy. So we really began by making mobile power packs for Hollywood filmmakers. This is under our Liberty Pack TM section of our company there. We made mobile power packs, and thinking about mobile products, these really are some of the hardest to manufacture, right? They have to withstand essentially an earthquake every day while you're driving, while you're carrying them around, while you're using them. And they also have to withstand just generally not the best treatment. Mobile products, I would say, is kind of proving our roots in being able to tackle challenging design and manufacturing problems. Whereas OES Energy was kind of our first residential storage battery. You can still see that logo on some of our products in the field today that are outliving their warranty. We then quickly moved into military and emergency response. So we convinced the military to do some testing of our lithium iron phosphate batteries because they really did not want to accept lithium proposals for the project they were working on. However, we convinced them that our lithium is not the same as all lithium. It's not going to be starting fires. You're not going to see it on the news. So just give it a shot and test it out. We convinced them to do that, and they were pretty happy and ended up using our product on the project after all. We actually still do emergency response today. So we have our IDEA program, and we definitely send out a lot of our units to be used in emergency response and just generally some off-grid applications where there wouldn't otherwise be power as well. So since 2013, we've been expanding our product line, always keeping in mind what the installer needs and what the homeowner wants. So we want to make it easy to get the job done. In 2015, we relaunched as SimpliPhi Power, and in 2017, we began ramping up manufacturing at our Ventura County, California location. We just expanded. Now we're in a second building on that same street. Why we're doing what we're doing is because there is a problem, right? That problem is not only escalating energy costs, not only failing infrastructure, but also a growing need for decarbonization. In the US, I've seen my electricity costs rise well over 15%, and European electricity prices are also expected to continue to increase by about 30% as they continue to phase out coal and nuclear. As we've been adding more and more EVs to the residential market, EV for electric vehicle, the transformers that the grid is installed are generally installed such that they're overloaded during the day and they cool off at night. But now as we're adding EVs, these transformers are not cooling off at night, and they're just causing a whole bunch of issues, overheating, unreliable power. So beyond being expensive, the grid is failing. And really, there's a growing need for decarbonization in many cities without a clear path for them to actually accomplish that goal. So hopefully we can be part of the solution towards decarbonization, making our infrastructure more resilient and keeping our energy costs locked in place and low. Got a question already on the lead time of our standard products. So check with our sales team, but it's extremely fast, so probably under 4 weeks, most of the time 2 weeks. All right, so an overview of today's content. We're going to be talking about AC and DC coupling, and this relates to how solar panels are actually connected to a battery bank. So no, unfortunately, I'm not talking about AC-DC music. I'm talking about AC and DC coupling. So coupling power from a PV array means how you're connecting it to a battery bank. So basically, you're either have some panels up on the roof with microinverters, and they're coming into another inverter and being converted back to DC power to charge the batteries, or you've got power coming in from a PV array as direct current and it's going through a charge controller of some sort and then connecting to the battery bank, staying direct current the whole time without being converted to alternating current at all. So those are the two ways you can do it. So we're going to start off by jumping into detail with DC coupling. So this means you'd have DC generation and then DC charging. So you'd have solar panels producing DC power, sending that power to a charge controller. That charge controller is going to control the DC voltage and amperage of both the PV array and the battery bank. So it's a powerful object here. When you install PV panels DC coupled, there's a lot of considerations to make. So it's not as easy as just tossing them anywhere and connecting them in any way you want. You really need to consider shading. So are there trees around? Because if you have a long series string of panels and one of them is shaded by a tree, all of those panels have no output essentially. As really you can look at this as a big water pipe of panels. And the panel that's shaded in the middle is like a valve that you're closing off, not allowing water to flow through the rest of the pipe or through the rest of the wires in the solar panels. So that whole string would go dead. Whereas if you had 5 panels in parallel and one of them was shaded, the other 4 would still produce perfect output, essentially. Another thing to keep in mind is you actually have to match the specifications of the charge controller. So if the charge controller is saying, hey, I can only operate under 250 volts DC, then you have to make sure your panels do not exceed 250 volts DC under any conditions, hot, cold, rain, sunshine, etc. And same with the current. So they'll have a maximum current that cannot be exceeded, and you have to make sure that that can't be exceeded even under no load conditions, you know. Keep in mind that cold weather is actually going to lower your open circuit voltage of your panels, actually makes the panels more efficient, and you really want to make sure that you have some wiggle room in your voltage of your string. So if your charge controller says that 250 volts is the absolute maximum it can have, you want to make sure you're shooting for, depending on your climate, maybe 200 to 225 volts as the maximum open circuit voltage under normal conditions, such that as it gets colder and that open circuit voltage raises, you have that wiggle room so you're not going to exceed that max voltage and break the charge controller. Now it is rare, but we have seen batteries damaged by over voltage events where the PV array was not properly sized to the charge controller, and the charge controller broke and let through that high voltage. That would definitely have the ability, depending on the voltage, to damage a battery bank. All right. So what does a charge controller do and how does it do it? I find it really interesting that the charge controller is able to regulate both the DC voltage and current going to the battery bank and maximize power production of the PV array or, you know, wind turbine, hydro turbine, whatever you're using. Now, it's regulating the DC voltage and current going to the battery bank simply by following the exact parameters that you, the user or installer, are programming into it. So that's quite simple. If you program 56 volts into that unit as the absorbed voltage and a 6-minute timer, it's going to hit 56 volts for 6 minutes and then shut off and go to float. Now, the power production of the PV array, that's a little more complicated. What it's going to do is it's going to sit So if you have an MPPT charge controller and your PV array, let's say, is sitting around 100 volts, that charge controller is then going to bump up to 100.2 volts and say, am I producing any extra power? No? Okay, why don't we go down to 99.8? 99.8 volts. Am I producing any more power? No? Okay, right back to 100, where I'm still producing the most power. So it's constantly tracking the point of maximum power by going back and forth and seeing where the maximum power is being produced in real time. These are up to 99% efficient. So really, you're looking at a minimal loss. That is why it is ideal to, if you're trying to charge a battery, not AC couple the PV array, because this conversion from DC to DC is very efficient, whereas converting from DC to AC back to DC, not as efficient. Now there's another type of charge controller called the pulse width modulation, or PWM for short. Now, instead of modifying the voltage to be 56 volts, for example, when you're charging a battery, it's just going to open and close that circuit using a FET very, very quickly. So many, many times per second. And maybe it has a nominal output voltage of 64 volts. And instead of jumping down to 56 volts, it just opens the circuit a few times per second to reduce the actual average voltage that the load is seeing. Now, if you were doing this real time with a switch, you'd never be able to achieve proper charging voltages. But using a charge controller that does this, hundreds of times per second, it's able to really make it so the battery only sees that average voltage that it's providing and not the full voltage. Now, this is less efficient than MPPTs in most conditions, but it's still a good fit for smaller systems that are, I'd say, 2 kilowatts, or really even less than 1 kilowatt. I would say PWM is a good choice. For all others, there's pretty much no question you want to go with an MPPT. Is there any good charge controller than MPPT? I'm not sure if I understand that question, Mr. Brown. So let me know what you're thinking there. MPPTs are generally the top of the line in terms of charge controllers, whereas PWMs are often seen as a little bit of an older, cheaper technology. Now, this diagram is purely here to demonstrate what lands on the DC bus bar. So everything, really the batteries, the charge controller, and the inverter, everything that's pulling or pushing power at 48 volts or 24 or 12 volts is going to be landing on that bus bar. Not the solar panels, but again, the charge controller and the inverter, plus any DC loads if you have them. But that's where they're going to land. They're going to land on that charge controller. And really, this shows me that some inverters claim they have a battery bypass feature, meaning that the charge controller can come in, the power comes in from the PV array, and without even having to charge the battery, it goes right to the loads. Now, if you look at the layout of this system, it's quite obvious that that can already happen. You don't need a special feature in the inverter to allow power to just bypass the batteries. Just going to use this bus bar to bypass the batteries if they're full. So if the batteries need charge, the panels will charge them. If the batteries are full, that power is going to go directly to the loads. Now, this is just an example of where sometimes that DC bus bar is not as obvious. You can't always tell exactly where it is. So like in this case, the DC bus bar is this combiner. If we wanted to, we could take this combiner away and land all the batteries on the inverter right here. So again, just kind of shows where the DC bus bar can be hidden in some cases. Now let's dive into AC coupling. AC coupling refers to either micro or string inverters, also referred to as PV inverters, because they're not providing power usually directly to the loads, they're providing power to the grid, or you can also call these a grid-tied inverter. So what these do is the microinverters will attach directly to a single PV panel or sometimes two PV panels and immediately convert that DC power being produced by the panel to alternating current. It's taking direct current, turning it into alternating current, and sending it to the grid or to a battery-based inverter. A string inverter is going to do the same thing, except this is not going to be on the roof. This is going to be on the side of the house, and there's going to be, many panels, 10, 20, 30, 40 panels going to a string inverter or a couple of string inverters. Now, string inverters and battery and microinverters, they're going to really do the same thing. String inverters are just a larger size version, and it's nice because if it breaks, you don't have to go up onto the roof and replace every individual PV inverter that you've got. Now, note that using a generator is basically the same thing as AC coupling. I mean, this is going to have an AC input to your battery-based inverter. We'll talk a little bit more about this, but it's really similar. I'm always curious about how the power coming from the PV array is controlled, how it's limited, how it's converted to battery power, etc. And really, a lot of that is handled by frequency shifting. So frequency shifting is a mechanism used by the battery-based inverter. So remember, you're going to have your microinverter or string inverter, you're going to have your battery-based inverter, and then you're going to have your batteries. So frequency shifting is used by the battery-based inverter to communicate with that PV inverter. So it's going to operate under normal conditions at 60 Hertz, providing a grid signal, letting those PV inverters know, hey, keep on producing that power, send it my way. These batteries want to charge up. Now, if the grid ever goes down and the batteries begin to get full and they don't want to charge anymore, the battery-based inverter can modify that frequency slightly, increase it by 0.1 Hertz, and tell those PV inverters to tone it down to produce less and less power. And then it can even increase the frequency in a large way, maybe by like 2 Hertz, 62 Hertz or something like that. And those PV inverters will shut off right away, so they won't produce any more power. So really, all this means that when you're installing a project, when you're going to a home that already has an AC coupled, or excuse me, a grid-tied PV array, they've got micros or a string inverter sending power to the grid, but they don't have batteries, and you're going to be adding that battery-based inverter, make sure you double check the age of those PV inverters, and double check that they're actually compatible with your new inverter that you're installing. So just give both companies a call, and they will know off the top of their head, this is compatible or this is not compatible. This is what I'm talking about by just a grid-tied PV system. So there's no batteries here. There's just solar panels on the roof. There's microinverters sending power to the main panel, to the grid. Now, if you wanted to go in and retrofit that, you could simply drop a system right between the sub panel and the main panel. Often installers will then route some loads, move them from the main panel and reroute them into the sub panel. So let's talk about some different applications and kind of debate where AC or DC coupling might be a better fit. All right, when you are off grid, so there's no grid present, you're out in the boonies, out in the mountains, in your cabin, in your van down by the river. Remember, DC coupling is definitely your best option. So if you're off grid, there's really no reason to convert that power to alternating current, because ultimately you're going to just be storing it in batteries right away. Now, some people say, well, what if I'm using that power right as it's being produced? If you're selling it to the grid as it's being produced, that makes sense. But if you're saying you're literally going to use it with your loads, that is very unlikely. If you look at the data your utility company provides you on when you actually use power, it is largely in the early morning before you go to work, and in the evening is really the heavy hitter, is the evening when you get home from work and you're opening your fridge, you're cooking on your stove, you're turning on your lights, watching TV, turning on your air conditioning or your heat, etc. So that is when you're using your power, is in the evening when the sun is down. So I would say that's really a misconception. So therefore, when you're off grid, DC coupling is almost undoubtedly the way to go. Even when you are on grid, I would say if you're installing a brand new system, it is most likely more efficient, ever so slightly, to do DC coupling. Now, I think this also gives you a little bit more control over where your power comes from and where it's going. It's very easy for an inverter to tell this power came from the DC side, it came from the PV array, it came from the battery bank. Whereas if it's trying to determine where power is coming from, a generator, AC coupled PV array, the grid, it's kind of hard to dictate there to determine where that power actually came from when it's all on an AC bus bar. So again, this definitely depends on your inverter, but I would say even in most residential grid tied situations, I would recommend a DC coupled system. Gives you a little bit more control over features such as selling to the grid, time of use, peak shaving, etc. Another thing is that when that grid experiences an outage, right? So your PV array, if it's a DC coupled PV array, has no idea what the grid is doing. That grid goes down, it doesn't care, didn't even notice. How would it even have been able to tell? I mean, it's on a totally separate side of the system. DC, PV, batteries, grid is over here. They're not touching each other. They're never going to know. The grid doesn't know if the PV's on. The PV doesn't know if the grid is on. It's just a seamless transition. Whereas if you have microinverters, when the grid goes down, that battery-based inverter is going to, it's going to need a few minutes to recalibrate. So those microinverters, when the grid goes down, they're going to turn off. And your battery-based inverter, eventually, once it senses everything is good to go, it's going to send a signal to turn those microinverters back on. So we'll talk a little bit more about that. When you want to AC couple, really this is mainly when there's an existing system. So if there's an existing AC coupled PV array, an existing grid tied PV array, just sending power right to the grid, just like we saw before here. So if you show up to a home and this is what you see, you might as well retrofit it instead of replacing all those inverters with a charge controller. I mean, what's the point? Another nice thing about AC coupled PV is you really don't have to worry about wiring concerns. So if you are a brand new PV installer, these are all going to be going in parallel at 240 volts. So they are not going to need a whole lot of consideration as to where you place the panels, how you wire them in series or parallel. It's just all the same. Each of these microinverters is going to optimize the amount of power coming out of each panel. And they also function as a safety device, shutting these panels down if they don't see a grid signal. So this is a very easy way to wire a PV array for a new person. And honestly, it's beneficial in cases where shading is an issue. So even if you're off grid, but let's say you've got trees all over the property, you can either use DC optimizers to mitigate that, or you can use microinverters. And maybe your installer is just more comfortable with microinverters. So really, that is totally fine. I would say AC coupling gives you probably more of a little efficiency hit. You're going to take a little efficiency hit there, as most of your power is going to be charging your batteries. That means most of your power is going to go from direct current in the solar panel to alternating current in the microinverter to direct current back from the battery-based inverter to the batteries. So you will take that extra efficiency hit. But aside from that, it is definitely an easier way to wire things up, especially in like much larger scenarios where you're looking at hundreds and hundreds of panels. This might be easier for you. To kind of just summarize, if you've got an existing PV array, you might as well just leave it however it is. If it's got a microinverter on each panel, great, put them to use. It's not that big of a difference. But if you're installing a brand new system, it is likely going to benefit you to do DC coupled, as long as there's not some crazy shading concern, or you are a novice installer. I would say to go with DC coupled in most cases. Now there is kind of a misconception here that AC coupled systems cannot have a battery on them for some reason. Grid tied PV systems. People used to think you could not add a battery or that it had to be DC coupled. Total misconception. You need a battery-based inverter to convert that AC power back to DC. There's also kind of a misconception that you have to replace the whole PV array. That is not true, but it is a lot of work to rewire the system. If you've got an AC coupled, a grid tied system, and you're going to go in there, lift up each panel and pull off that microinverter and then wire the panels in series or parallel, that is a lot of work. At that point, you're close to the same sized bill from the contractor that you'd get if you did rewire the whole array. Excuse me. Let's talk about rapid shutdown. Rapid shutdown is really going to be required by just about every jurisdiction. There's very few places that don't require rapid shutdown. And what rapid shutdown is this is a device that a firefighter can use when they show up to your house to put out a fire to immediately turn off that PV array, hopefully in the flip of one switch or the click of one button, to terminate all power production and all power flow from the PV array. And even in most jurisdictions, they're now wanting to see the battery able to be disconnected too. They do not want firefighters, swinging an axe on a roof and hitting 600 volts from an array and becoming toast. So really what this means is in any jurisdiction, you're going to need to contact your AHJ, your authority having jurisdiction, and figure out what they want to see in terms of safety for your rapid shutdown system. Many will allow you to get away with just a shut-off box if your PV array is ground mounted. So if it's not on your roof, you probably just need a disconnect switch that they can easily access. If that PV array is on your roof, you're gonna need a module level shutdown. So you're gonna need either a DC optimizer that will turn off automatically when you press that button, or you're gonna need a rapid shutdown attachment. That rapid shutdown attachment serves only one purpose, and it is to turn off when it does not see a signal from your transmitter. So you'll have a transmitter that attaches around the wire that goes to the PV panel, and it sends a keep alive signal. So kind of like a pulse every few seconds, basically, to that rapid shutdown attachment that's actually on the back of the panel. And if that rapid shutdown attachment on the panel does not see the transmitter sending that pulse, it's going to turn off. It's going to shut down that PV module. Some other options here, you can get really creative. Midnight Solar makes a remote trip breaker that you could install. For example, if your system, you want to be able to access it from indoors, you want to shut everything down from inside, you could use a remote trip breaker that would then turn off a breaker that's maybe somewhere else on the roof or outside. And there's a single button shutdown capability now as well. So many inverters are going to have a single button that you can press to turn off everything in the system. PV array, disconnect batteries, turn off inverter, etc. Now, for an AC coupled system, if you've already got the PV array up and permitted, then adding a battery-based inverter is not going to change the rapid shutdown compliance of that existing PV array. So if you've got microinverters on each panel or a string inverter, that's going to handle your rapid shutdown compliance for the PV array. That's not to say that your jurisdiction might not require you to do a battery-based shutdown. That could happen, but they should not require you to change what's already safe on your PV array. They should allow you to just leave that how it is. Even if the codes have been updated, remember, you're not touching the PV array. So that's already been permitted, it's already done. You're only adding a battery. This is really just an example of what you'd see. So you'd have a shutoff box, really just a disconnect switch for your PV array, and you'd have that single button shutdown that you can press to turn off the output. In an AC coupled system, you maybe just need a shutoff box. So this depends if your jurisdiction is going to require battery disconnect or not. So in this DC coupled scenario, that red button, that's going to disconnect the batteries, it's going to disconnect the PV, it's going to turn off the inverter. In this scenario, this is just turning off the PV. So really there's no way to disconnect these batteries except for turning them all off individually, not something a firefighter is going to have time to do. So some jurisdictions may require additional protection. All right, so more system design considerations. Let's talk about PV sizing. A lot of people like to really oversize their array for those cloudy days. In a DC coupled scenario, it's very easy to have a very, very large array and limit those amps that are charging the batteries through the charge controller. You just program in, hey, I don't want to charge the batteries faster than 60 amps. That charge controller says no problem. And it's very reliable and it sticks to this amount. One thing though you will have to keep in mind, of course, is the layout of the PV array. So I mentioned shading, keep shading in mind. You also have to think about wiring runs. So if you've got 100 feet between your ground mount and your house and your charge controllers in your house, then you got to remember that's a that's a long wiring run. If you've got 12 gauge wire, you might see a drop of like 5 to 10 volts across that wire. So make sure you have the right size wire. I have yet to see anybody use less than 10 gauge on a residential install for DC coupled, but I know a lot of people are upsizing, maybe even 8 gauge or even 6 for a very long run for maybe a ground mount a long way away from the charge controller. Again, when you're DC coupled, it doesn't care, the PV array doesn't care if the grid is on or not. It's just going to do its thing and charge the batteries, and the batteries are going to do their thing and power the loads. Whereas when you're AC coupled, remember when the grid goes down, if your PV array is just grid tied, and you don't have batteries and the grid goes down, you are not producing any power and you don't have the ability to back up your loads. As soon as you add a battery to that system, you do have the ability to continue to produce power in an outage and to continue to power your loads. But it's going to come down to that battery-based inverter to send that signal, that keep alive signal or that grid signal to the PV array. Say, hey, turn back on, please keep charging, we're all set. Advantages of AC coupling, really just to summarize, is that it's easy for wiring. There's really no shading concerns. The microinverters are going to handle everything. If you're using a string inverter, you do still need to consider shading, and you do still need to consider wire runs. But if you're using microinverters, this is really something you don't have to think about. You just kind of connect them all together and they do their thing. You don't have to worry about thinking through to the design extensively. You just connect everything in parallel. Each panel is optimized by the micro. No need to worry about string size or wiring size, and it's just a simple install. Lastly, well, not lastly, but getting towards the end here, want to talk about key features of our products. So our battery is lithium iron phosphate chemistry and cylindrical form factor. So this is how we build our products. It is the safest way we can possibly think to build them, and we're always building them safer. We have several safety certifications from third-party testing companies. Underwriters Laboratory is a company that creates testing standards and performs those tests on products, certifying them as safe against things like fire. So 1642 is a cell level certification, 1973 is a battery unit certification, and then 9540 that certifies a whole system, battery, inverter, charge controller, etc., as safe and able to operate together. Whereas 9540A, so that's a kind of a subset of 9540, that is actually a fire testing protocol. That is, this company basically tried to light our product on fire and was unable to do it, so we pass, right? So that's wonderful. It's extremely safe. This means it's basically impossible for our battery to be the cause of a fire that lights up your house, right? Even if your house is on fire, it's going to have trouble burning these batteries up with it. They are that safe. You are going to need these UL certifications for things like meeting building and fire codes, getting your system inspected, getting your insurance to actually cover anything that's happened to your home. And of course, you should check with your AHJ to be sure you know exactly what is required. So here's an overview of what we offer. This is our standard 3.8 kilowatt hour battery. This is able to be AC or DC coupled. So the battery does not care whether you're AC or DC coupled. It is going to receive DC power, whether it receives that power from the charge controller or the battery-based inverter, it doesn't care. You will need a battery-based inverter for either case. So really though, if you are doing AC coupling, frequency shifting, and really almost all AC coupled inverters require a 48 volt battery to operate properly. There's not a lot of 24 volt batteries on the market that even work for grid tied systems. Our SimpliPhi battery is really the same 3.8 kilowatt hour, 48 volt battery. However, this is now with communications added. So it is able to intelligently talk to certain inverters, such as our SimpliPhi ESS inverter, SolarArc inverter, and Sunny Island. So that's going to report accurate real-time info, such as stated charge, voltage, temperature, and current readings. our access unit. So this is batteries and an inverter and a charge controller inside of an outdoor rated NEMA 3R cabinet, pre-wired up for you. So this is really a good option for AC coupled systems, as all that equipment is already outside. So adding an outdoor rated unit to an outdoor system is very easy. You don't have to punch any conduit through the walls. You don't have to use any pass-throughs. It's easier to source the small parts and pieces that you need, having this cabinet with knockouts already on the side, for example. It's also UL 9540A certified and UL 9540A tested. So it's extremely safe, and you're not going to run into issues with this being, not approved by your inspector. There are PV limits, so keep these limits in mind if you're AC coupling PV to one of these units. We also have our new ESS system, energy storage system. So this is a 6 kW inverter, 4.9 kWh battery, and an energy track control system and app. This app is going to allow you to monitor the system remotely, make programming changes from the comfort of your home as the installer. It's going to allow you to see, as both the installer and the homeowner, the power flow between different devices, and it's going to allow you to see historic data, what's happening to your system, push notifications for fault codes and warnings, etc. And it's also going to have over-the-air firmware updates, which is a really nice capability. This can be scaled up to 9 inverters. So each inverter can do both AC or DC coupling. This is a 6 kilowatt inverter. So if you've got 9 inverters, that means you can have a total of 54 kilowatts of AC coupled PV. And it also has a charge controller built in 7.5 kW charge controller in this unit. So that is a major plus. Whether you're AC or DC coupling, this is the one part you need. This is the one inverter you need. It's not going to, you're not going to need to add a charge controller or a separate inverter. You can AC couple right to this. This is also outdoor rated. So it's, maybe deceiving because it has this screen here and you think it's not going to be outdoor rated, but it is definitely outdoor rated. You can use this outside. It's IP65. We've also got the 4.9 kilowatt hour battery that is also outdoor rated, and you can scale this up to 72 batteries per system. So that's up to 358 kilowatt hours. And then if you're using the inverter, 54 kilowatts in one system. The Energy Track app also, as I mentioned, major highlight, you can commission the system just by using the buttons on the inverter if you don't want to have a gateway and an internet connection. But if you do want remote monitoring and a faster commissioning, I highly suggest it. You're just going to need to download an app and purchase a gateway that's going to provide internet to your inverter. Now, if you're confused about anything that I've presented, first off, I'm going to get to the questions very shortly, but also we've got a boatload of design help here. We've got a bunch of sizing tools on our website. We've got a battery sizing tool, a system sizing tool, and a lead acid replacement calculator for adding batteries to a system. Beyond that, we've got manuals, spec sheets, and integration guides. These are really helpful. So especially our integration guides, they're going to show you, let's say you've got a Midnight Classic charge controller and there's a setting, you don't know what it means, but it's called EQ. So you go into the integration guide and you see we've listed EQ and the exact value that you should set EQ to. So that is why these integrations are so helpful. These integration guides have been developed over years and years of our techs actually using the equipment, going in and our engineers in the lab actually using the equipment, writing down the names of these settings, and then writing down the values that you should set them to. We're also available by phone, so tech support is 805-640-6700, option 1, and sales is just option 2. Same number, option 2. So give us a call and we can help you out. I would encourage you to give us a call right after this training. If you have any projects and any questions you're working on, we will be on the phones. I want to touch on our Elite Installer Qualification Program. If you are already installing our batteries, this is a no-brainer. You need to sign up ASAP. As an installer, you'll be highlighted on our map as a place where customers can go to buy our products. This is also how our sales team routes installers to customers. They will look at this map and say, oh, the nearest 3 installers to you are these 3 people. Here you go. Here's a link to their website. Here's their phone number and email address. You can also earn $25 per battery cash back. So email me for any details on how you can become IQ qualified installer, or how you can join our Elite IQ program and become a SimpliPhi certified installer. All right, so I'm going to jump into answering some questions here. Don't hesitate to email me or give our sales team a call with any questions, or if you need NAPSIP credits. Good question. Yes, all attendees will automatically receive a copy of the recording of this presentation. Yes, we will issue NAPSIP credits. Just email me your full name and say, hey, I'd like NAPSIP credits. My name is blank. Good question, Anton. Inverters. So if you have 5 inverters in the system, they will all share the same battery bank. You do not want a separate battery bank for each inverter, just one battery bank in total. If you're retrofitting an existing grid-tied system, is there a rule of thumb to expand the PV array to fit the battery capacity to make sure the batteries are charged and used according to our needs? So that's a good question. I'd say it's a little bit more complicated than a snap of the fingers. What you're going to want to do is make sure that your PV array is producing enough power to charge the batteries, really just enough to cover your loads. So if you're in an area that has 6 sun hours each day on average, and you've got a 5 kilowatt PV array, then 6 times 5 is 30 kilowatt hours. So you should have enough power to support up to 30 kilowatt hours of electricity use, or charge the batteries up to 30 kilowatt hours. So really this is based on the loads, I would say. Sizing the PV array should be more based on the loads than the battery bank. If your customer has, a 50 kilowatt hour daily energy usage on their utility bill, and your PV array is only producing 30 kilowatt hours a day, then yeah, maybe double that PV array size. For NAPSIP credits, Michael, please email me, walker.matt@basco.com, because we're having an issue with our email, our SimpliPhiPower.com email. Thank you for your understanding there. When you're using a microinverter, you do need a battery-based inverter to charge a battery. When you're using a microinverter just to send power to the grid and you don't have batteries, that's fine. You don't need a battery-based inverter. What is the DC optimizer and what conditions can one use it? So a DC optimizer is much like a microinverter. You're going to attach one to each panel, It's going to optimize the power production for that panel, very similar to an MPPT. And if that panel is completely shaded and has no output, it's going to just short that panel out so that other panels in that string can continue producing power. So really, a DC optimizer will mitigate any concerns of shading. If you have trees on your property that you're concerned will affect the production of your array, a DC optimizer is a great solution there. So you can use that on any DC coupled system as far as I know. I have not heard the term reverse DC coupling, so I'm not sure what that means exactly. It's a good question. To find the charging parameters for a Schneider MPPT 60-150, you can check out our integration guides on our website. So that'll be under the support tab on our website. Any other questions? Throw them in there real quick. Give another minute for questions. All right, thank you everybody. Thanks for joining. I'll send out the recording in about 24 hours. And again, email me if you need NAPSAP credits. Have a great rest of your day. Thanks for coming.